In our last lecture, we were discussing about the stereogeometry, and basically we have seen the analysis for this search range. The basic purpose of that was given a point, a candidate point in one of the images, let us say the left image, how to find its corresponding point in the right image. That is to say that what is the total search area, and we had discussed that instead of searching over an entire n by n pixel space, one can search just over a line on which the corresponding image is constrained to lie. And thereafter, based on the stereogeometry, we had seen that one did not have to search for the entire line, okay, rather one can only search over the part of a complete line, so that one can search for the corresponding image point, okay, on the other image. Okay, so we were we had derived all the expressions for search range, okay, and today we will spend some time to discuss about the spacing between the two cameras, because you remember we had in our expression, we had the expression delta x, okay, which was primarily controlling the unknown depth z0, that was heavily dependent upon this delta x, that is the separation between the two cameras. And even in our expression for search range, we saw that this delta x was coming in the picture again and again. So now the question is that what should we keep as delta x? Should we keep it too small, or should we keep it too large, or anywhere in between? Okay, so let us try to analyze that aspect, that what should be the how should we decide about delta x, and what should be the criteria for those decisions. Right, now in our last class we were considering a geometry of this nature, and basically there what we did was, this was our left image plane, this was the right image plane, and then we had drawn the rays passing through the extreme end of the left image's plane through the optical center CL. We had joined that ray, okay, and let us say that it intersects the plane which we had defined to be the maximum depth position. So this D or D max we were calling last time, this was the maximum depth, okay, as measured from the optical center. So this ray LCL was intersecting this plane at L, okay, and similarly RCR was intersecting this plane at the point R prime, okay, and then we had joined R prime with CL, and basically R double prime was the point where we were having the point of intersection. So basically, if you remember, we had discussed in the last class that our PL, okay, PL should lie within the segment LR prime, LR double prime, so that it is visible in the other image also. It is very clear from this diagram that supposing if PL lies on L, okay, then we have this ray going out, okay, and then provided the point is in the the point is three-dimensional space was in the region R prime S L prime, okay, we would be getting its corresponding point in the right image. So in the extreme case, when L was over here, okay, we were getting the corresponding point at R if the three-dimensional point happens to be somewhere here. But for other three-dimensional, for three-dimensional point, that is to say the actual point in the 3D space, if it is in other position, then we can get its position by joining that point with the optical center of the right camera CR, and by extending that ray we can find out that at which point it is intersecting. So basically the condition is that this point PL should lie within R double prime L. Now supposing if PL lies in the range R double prime E, okay, in the left image, okay, then what is happening to it? Correct. The correct answer which some people have given is that if PL lies within the zone R double prime E, okay, you can clearly see from this picture that it is not possible to get its corresponding view in the other image. Alright. Now, if it is within this range, that is to say, if PL really lies within L R double prime, then the question is it guaranteed that we are going to get its corresponding point in the other image? Well, just take PL a point like this. We are taking a point PL which really lies within LR double prime, and this PL we are joining the optical center CL with PL and extending the ray like this. Okay. Now, if the point in space, the point P in the three-dimensional space may lie within this zone R prime CL S. Supposing P exists within the zone R prime S CL, then what happens? Then can we see the point in the other view, in the right view? We can't see it. If the point P lies within this zone, okay, the point in space lies within this zone. That means to say, by extending this straight line, if the point lies anywhere over this area, we are unable to get its corresponding view in the other image. Only if P lies within the zone R prime S L prime, okay, then we can see the corresponding image point in the other image. Alright. So that means to say, the primary condition, so there are two conditions. Firstly, that the point PL must lie within this zone LR double prime, number one. And then the number two condition is that even if PL lies within this range LR double prime, okay, the corresponding point in space must not lie within the zone R prime S CL, rather it should lie within the zone R prime S L prime, so that it is visible to the other view. Now, in the last class we had discussed one aspect, that if there happens to be an occlusion, okay, somewhere over here, so that the ray from the three-dimensional point to the other view gets blocked. If there is any occluding object, okay, in that case we will not be able to see the point in the other view, despite the fact that it is existing within the zone R prime S L prime. Is it very clear to all of you? Alright, so let us now translate this condition. So the primary condition is that PL must lie within L R double prime. What is the coordinate of L with respect to IL? Because we have been all along taking IL as the center of the coordinate system. Origin of the coordinate system is being taken as IL. So what is the x dimension of the point L? It is h by 2 plus h by 2, because the positive x direction is this one. This is taken as the positive x direction. So the point L is having an x coordinate equal to plus h by 2. Whereas the other point, the other extreme, that is to say R double prime, okay, we can determine the distance of IL R double prime again by applying this geometry, knowing fully well the fact that delta x is the distance of separation, okay, lambda is the focal length of both the cameras, d is the maximum depth, okay, from the optical center, okay, d being the maximum depth. Then we can determine the dimension of this or distance of this IL R double prime, okay, and if we do that analysis, okay, simply from this geometry, then the expression that we get is that basically PL's x coordinate is being defined as XL. Okay, that you remember, XL was the x coordinate of the point PL. So in one extreme PL must lie, rather XL must lie, must be less than h by 2. That is to say, when we are taking the point PL to the extreme end L, okay, it must be less than or equal to h by 2. And at the other extreme, okay, that is to say, when PL is being shifted towards this point R double prime, then corresponding to this R double prime, the limit which we get is, okay, it is minus h by 2. If it is minus h by 2, then PL could be taken all the way up to E, up to this point E, okay, this extreme point. But we cannot take it up to E simply because of the fact that we have already assumed a maximum permissible depth D. So since we have assumed that maximum permissible depth, we cannot take PL up to E, rather a distance of minus h by 2, but it should be a distance little less than minus h by 2. So it will be minus h by 2 plus, if you are doing the geometrical analysis, okay, it works out as lambda delta x divided by d. Okay, or you can simply write it as follows. You can say minus dh minus 2 times delta x lambda divided by 2d, okay, is less than or equal to XL is less than or equal to h by 2. Now basically these limits of XL which we have got, okay, basically signifies, okay, that what should be the range of XL for which the corresponding point can be viewed in the other image. Of course there are other conditions as well. The other condition, as we said, is that it must lie within the zone R prime SL and there must not be any occlusion, okay, for the corresponding ray, okay. But assuming that those two conditions are getting fulfilled, still the basic condition which PL must fulfill is this. Now you think of various possibilities, okay. Like I said that we are going to study that what is going to be the effect of delta x. Now you make, for this expression, you make delta x equal to 0. 0 means what? Physically what does it mean? It no longer becomes a binocular view, rather the left view and right views are simply merged, okay. So that is a degenerate case, of course. But taking delta x equal to 0, if you substitute in this expression, then the range of XL is minus h by 2 to plus h by 2. So that means to say that if you reduce the spacing of the two cameras, okay, gradually, and make it too small, okay, then what you are getting is that the range over which PL can lie, okay, so that it is visible in both the views, okay, is quite large, okay. That means to say that the common field of view is increasing as you are reducing the spacing between the cameras. What is meant by common field of view? In this particular diagram, this being the left image, this being the right image, in this particular diagram, whatever I am shading right now, okay, this zone R prime SL prime, this is the common field of view. Field of view is very often written in short form in literature as FOV. So the common field of view FOV is this zone. Now you can very clearly see, if you reduce the spacing between the two cameras, okay, the delta x distance, if you reduce, then this zone naturally increases in its size. So the common field of view increases. So that means to say we have a better possibility of having a binocular view for image points. Okay, it is, there are much better chance of finding the corresponding point in the other view if we reduce delta x. The common field of view increases. Alright. Now, so one conclusion which I should try to draw at this stage is we should have delta x as small as possible. Alright? But let us see whether this conclusion remains valid always. We will do the analysis from some other consideration. You remember we had derived the expression for the left camera and the right camera. Their geometrical relations were derived over here. Equation number 1 and 2. This we had already seen, I think 1 or 2 classes back we had seen this, and from this we could compute z0, okay, which was given by lambda plus lambda del x divided by xl minus xr plus delta x. This denominator term is known as the disparity, so z0 was inversely proportional to disparity. We had seen that. Now basically this expression for z0 is going to be correct provided for a point PL whose coordinate is xl, you have accurately determined xr. If you have accurately determined xr, then only you can say, and provided we assume that delta x is accurately known, lambda is accurately known. If we make those assumptions, we can always say that z0 is accurately measured. Alright. But basically while measuring xr, we may make some mistakes. Let us say that this xr which we are getting, okay, is not really xr, rather it is xr plus epsilon, where epsilon is a small error which we are making in determining xr. So if we make a small error in xr, naturally that results in an erroneous depth. So let us have the expression for the erroneous depth, okay, by applying the same formula, okay, and I would call the erroneous depth as z epsilon. So z epsilon will be equal to lambda plus lambda delta x divided by xl minus xr. So far whatever I have written is same as the expression for z0, but simply instead of writing xr, I would write xr plus epsilon, xr plus epsilon plus delta x. This is the expression I got for the erroneous depth. Let me call this as equation number, the original z0 expression as equation number 3, and the erroneous z0 as the equation 4. So if I substitute z0 from z epsilon, then that is going to give me the depth error which I am making. Alright, so that is what we are going to compute, but it is better not to compute it, rather it will be inconvenient if we compute it in terms of all this xl, xrs, etc. Rather than doing that, we very well know that there is a relationship between xl and xr already. By examining this equation number 1 and 2, we see that there is a relation between xl and xr in terms of x0. So if xl and xr relationship we can represent in terms of x0, then we can represent equation 3 in terms of x0, equation 4 in terms of x0, so that we represent the error also in terms of x0. So very simply by from equation number 1 and 2, we see it is x0 by xl equal to x0 plus delta x divided by xr plus delta x. Alright, and from this expression what we conclude is we get XL minus XR plus delta X. Mind you, this expression is very much important to us. I mean, if you take this expression, then from here you can derive that XL minus XR plus delta X. This term is very useful. What is this term? Can you remember? This term is the disparity. So this is equal to, the disparity can be expressed as minus XL delta X divided by X naught. So what I will simply do is that, if this is the expression for the disparity, I will simply substitute, let me call this as equation number 5. I will substitute this XL minus XR plus delta X as I get from this equation 5 into equation number 3 and in equation number 4. Okay. So if I substitute this in equation number 3, okay, what I get for Z naught is, I get Z naught as lambda minus lambda X naught divided by XL. And if I substitute this XL minus XR plus delta X is equal to this expression, equation number 5, in equation number 4, okay, I can substitute everything for XL minus XR plus delta X. Only this epsilon term will be remaining. So by taking that epsilon, by taking that epsilon term, what I get is, for Z epsilon, I get it as lambda minus lambda X naught delta X divided by XL delta X plus epsilon X0. Okay, so I have represented Z naught and Z epsilon in terms of X naught, XL, lambda, delta X. Any questions? Equation number 5? Okay.
So the one which is circle, you got it after substituting X naught and
one which I have circled. Well, I get this directly from equation number 1 and 2. You just see that 1 and 2 is having, the third expression is lambda minus Z naught by lambda for both 1 as well as 2. So that X naught by XL is equal to X naught plus delta X divided by XR plus delta X. That is exactly what I have written. Any doubts there? Equation number 5. Alright, equation number 5 I am getting simply from this expression. I am just simplifying this. Just by a simple simplification of this, you just multiply this X naught with XR plus delta X, and that becomes equal to XL into X naught plus delta X, and then take the XL minus XR plus delta X term on the left hand side, you get simply this expression.
Z naught is equal to lambda minus
Z naught is equal to lambda minus this expression. Okay. What all that I am doing is XL minus XR plus delta X, I am just substituting this minus XL delta X by X naught. And my original expression was Z naught is equal to lambda plus this. So in place of denominator, I am substituting minus XL delta X by X naught. Okay. So what do I get? I get Z naught as lambda minus lambda X naught by XL. Is that clear to all of you? Okay. Simply a substitution. XL minus XR plus delta X, instead of writing such a big term, let me do it for your convenience. This is lambda plus lambda delta X divided by, instead of writing XL minus XR plus delta X, I am writing minus XL delta X divided by X naught. Okay. So that this expression becomes lambda minus lambda delta X X naught divided by XL delta X. Delta X cancels out, and you get lambda minus lambda X naught by XL. Is that clear? Very similarly for Z epsilon, what I am simply substituting is XL minus XR plus delta X. Okay, I have got this epsilon term only outside, and this is what I get after substitution. Alright, okay, I call this as equation number 6, I call this as equation number 7. Okay, so what I am interested? I am interested in finding out the depth error. So the depth error, okay, should be written as, let me call that depth error as S of LR. Okay, depth error is equal to Z epsilon minus Z naught, and again if you are just subtracting Z naught from Z epsilon, what you are getting is, I am just writing the expression after simplification, and the expression which results is epsilon lambda x naught square divided by XL delta x plus epsilon x0. Okay, you can verify this result. It is very clear. Z epsilon minus Z naught, lambda and lambda cancels out, and what results is this. Now, what is this SLR? That is the depth error, and the depth error is very much proportional to delta x. Alright, SLR is really dependent on delta x. Let me, instead of writing it as delta x always, I write W for delta x, and in that case my SLR, okay, can be written simply as a function of W. Okay, so let us study this depth error as a function of W, W being the distance delta x. Let us see how it changes with delta x. So simply what I get is, now this is my expression, and my starting expression is epsilon lambda x naught square divided by XL into XL W plus epsilon x0. Simply from this expression, all that I have done is, instead of delta x I am writing W, and instead of SLR I am writing f of W. So f of W becomes equal to this expression, and I am interested in studying how this f of W changes with W. So what I will do now, I will simply differentiate this FW with respect to dW. So what I get after differentiation is dFW dW is equal to minus epsilon lambda x naught square divided by XL W plus epsilon x naught square. Now in this expression, just see everything, epsilon lambda x naught being in this case a square expression, it is x naught square, XL plus x naught over here, again the denominator is a square term, so everything over here is positive and everything is with a negative sign. So dFW dW decreases for all values of W. I repeat, dFW dW is a decreasing function in W for all values of W. So what is the conclusion from it? As W increases, I repeat, W increases means the separation between the cameras increases. If W increases, what happens to the depth error? The depth error decreases, and the opposite is also true. If W decreases, that is to say, if I reduce the spacing between the two cameras, the depth error increases. So what is the conclusion that I should draw about my delta x if I consider the depth error aspect? I should have W or delta x as large as possible. So from here my conclusion is from depth error consideration, W should be as large as possible. And for increased field of view, W should be as small as possible. For depth error consideration, W as large as possible. For increased field of view, W as small as possible. So all that we have to make is a trade-off. If you make W too small, okay, you are increasing the field of view, but the depth error at the same time increases. If you are increasing the spacing between the two cameras, you are reducing the depth error, but at the same time you are also reducing the common field of view, or rather the overlapping in the two views will be less and less as you separate the cameras out. Any questions on this?
Here, while checking this, depth error reduces and increasing the view. It assumes that the error in terms of size is only positive. What if the error is on the other side?
Alright, basically what we are assuming, see, I have always considered that XR is not XR, but XR is XR plus epsilon. Okay, and really speaking, I am considering, so there is nothing wrong. I mean, if you are substituting the epsilon value, if the epsilon value happens to be negative, no, it does not increase. Okay? Anybody can give a correct answer to this. It does not increase.
Okay? Equation for differential equation for
is a differential equation. Yes.
If you put epsilon is equal to say minus x or minus t somewhere,
okay,
then it becomes a positive expression. That means it is increasing.
Can you see the paradox yourself?
Yes.
Just explain what is the paradox.
This is the denominator.
It is in the denominator. Okay? Okay, so these are the basic problems in the lateral stereo. Okay, that you are, I mean, it is very difficult to decide about the W. You make it too small, you land up in the problem of increased field of view. I mean, you land up in the problem of reduced, increased error, and you make W too large. Okay, it results in increased field of view. Sorry. I mean, I just conclude it once again. W small means, okay, your increased field of view, which is better, increased FOV, which is better, but increased depth error, which is a negative point, and W large means decreased FOV, which is a negative point, but decreased depth error, which is a positive point. Is it clear? Alright. So this basically concludes our discussions on the stereo geometry. Now what we have discussed in the last 2 or 3 lectures is mostly the geometrical aspects of stereo. So we have only analyzed, okay, the situation like this, that if we get a candidate point PL from the left image, then what is the range, search range over which we find out, or we can find out the corresponding point PR in the right image. Okay, we have analyzed this aspect very thoroughly, and we have also seen the expression for the depth error today. But one point which we have said, I mean, which was in fact brought out during the discussions in the last class, somebody had said very rightly that if we get a candidate point from the left image and if a search range is defined, okay, then in that search range we can get multiple number of candidate points in the right image. So how to decide that which is the correct match? And that problem I told in the last class is the problem of stereo matching or stereo correspondence, and this problem we did not address in this class, okay, because basically we are yet to cover the all the basic image processing operations, how to perform the edge detections, how to perform the feature detection, analysis of features. All these things we haven't yet considered. So that is why at this stage I am not discussing about the stereo correspondence, and it is unlikely that we will find time to discuss about stereo correspondence in this series of 40 lectures. But I can suggest some reference to you, very useful reference, which you can refer to know about stereo correspondence. The references are on the stereo geometry, okay, a very useful reference is N. Albertos, D. Brazakovic, D. Brazakovic and R.C. Gonzalez. The title of the paper is Camera Geometries for Image Matching in 3D Machine Vision. It appeared in IEEE Transactions on Pattern Analysis and Machine Intelligence, Volume 11, Number 9, September 1989, page numbers 897 to 913. Stereogeometry, the reference N. Albertos, D. Brazakovic, R.C. Gonzalez. The title of the paper, Camera Geometries for Image Matching in 3D Machine Vision. It appeared in IEEE Transactions on Pattern Analysis and Machine Intelligence, Volume 11, Number 9, September 1989, page numbers 897 to 913. On stereo correspondence, I have suggested two useful references. Although it will be better for you if you go through these references after you have a background on the edge detection and low-level image processing operation. It will be better for you to understand these papers. The author for these papers are, the first paper, it is by David Marr, D. Marr and G. Poggio. D. Marr and G. Poggio. Incidentally, D. Marr and G. Poggio had worked in the Artificial Intelligence Laboratory of MIT in USA, and they were one of the pioneers who had worked on the theory of human stereo vision, and their human stereo vision algorithm, which was later on implemented by their student W.E.L. Grimson, okay, still whatever research is being done in the field of image processing, many a times the major motivations are drawn from the pioneering work of David Marr and Poggio. Okay, so they had worked in MIT Artificial Intelligence Laboratory. The title of this paper is David Marr and T. Poggio are the authors. The title of the paper is A Theory of Human Stereo Vision. A Theory of Human Stereo Vision. It is published as a memo from the MIT Artificial Intelligence Laboratory. MIT Artificial Intelligence Laboratory memo number 451, and it was published in November 1977. A computer implementation of this theory was presented by Grimson W.E.L. Okay, the title of the paper was A Computer Implementation of a Theory of Human Stereo Vision. A computer implementation of a theory of human stereo vision. It appeared in the Philosophical Transactions of Royal Society, London, volume B 292, page numbers 217 to 253. It appeared in 1981. And subsequently, a number of research workers had worked on stereo correspondence. In fact, stereo correspondence happens to be one of the very active areas of research even now, because the stereo correspondence problem is not easy, because you have to find out a proper matching, okay, out of a large number of candidates. So there are possibilities of false matchings, or rather ambiguous matches. There are also possibilities that some of the points will not get matched at all with the corresponding points in the other views. So unmatching problem, false matching problems, these are very much there in the stereo correspondence, and a lot of people are still working. I mean, still the solution is not 100% foolproof. There are a number of ways by which stereo correspondence can be done. Some research workers have done it by comparing the intensities of some specific feature points. I mean, intensities over a neighborhood, intensity or the statistical functions of intensities defined over a neighborhood region, okay, taking that as a matching criteria. Okay, some people have studied those effects for the stereo correspondence, and some people also worked on feature based stereo, in which instead of trying to match on a pixel by pixel basis, you match only some specific feature points. Let us say after you detect the edge or the boundary of an object, take only those edge pixels or the boundary pixels and then try to perform a matching for those points. Okay, so feature based stereo has in fact I mean, ever since the availability of low priced computers and very high performance computers, okay, people have worked more and more on the feature based stereo, and very powerful algorithms, okay, exist today on the stereo correspondence. Okay, this is a good starting point. If you would like to know more about stereo correspondence, please go through these two basic papers, okay, and then all the recent issues of pattern analysis, machine intelligence, computer vision, graphics and image processing, and all other image processing journals like pattern recognition letters, etc. Okay, if you scan their issues over the last 5-10 years, okay, you will find that a number of algorithms have been suggested for stereo correspondence. All right, any other questions? Thank you.